This is the second lecture in this series, Differential Geometry, Analytical Mechanics, and Economics. And I got a bunch of questions after the last one that ended up changing my mind a little bit in the way I'm setting it up and where I'm paying attention to. So originally, I was doing the usual thing where when you say, all right, we need manifolds, and then, you go ahead and you put it all up, and then you give one or two examples quickly like that. Hey, they're important because here is a standard example that everybody gives. And then you go on and then you just pretend nothing happens. And it leaves everybody guessing as to why this is all useful and, now what you can really do with it. And I decided to, and also it makes it so abstract. And the only way you can understand it is going back to your regular flat spaces and pretend there are no manifolds, and then somehow understand it and then say, oh, okay, but this is more general. And I really want to get away from that, all right? Because I fell into the same trap that I hate that everybody else put up for me when I was studying this stuff. And all the work still has to be done in like identifying real problems that intrinsically make use of this manifold structure, okay? And as it turns out, especially economics gives you fantastic applications, I feel. They're everywhere. It's just that we're getting so used to dealing with everything linearized around a point and then making our our port system or whatever, multi-port system, and then be done with it. But this is really worth your while to get through it and make you can go beyond that and also see which point around which you're linearizing. Okay. So I redid the slides a bit. The first slide I didn't redo, so we don't need to go through that anymore. We all know the story. And I added a slide here. Last lecture I started over here telling you how you had time, and then you do your execution, and then somewhere in here is something fuzzy, the economic states, and then you do your reporting, and then you make your statements. But I wanted to back up a little bit and just say why is this so useful? So what this space does, this tangent bundle, is keep track of all the trade that's going on. So as you know, last time I said there are n agents and there are d number of goods, okay? This gives you a total of n times d, n times d degrees of freedom, all right? Okay. So that all sounds abstract, but now look at this picture. I just got this from the internet. I just typed in economics and trade or something, and out comes this picture. So you can actually see the agents here. Here's an agent, here's an agent. There's actually a dog that considers themselves an agent, all right? So you can count them. I actually didn't. There's quite a few of them. And then you can see all the goods. So this one, this lady has bananas. This guy is hawking some books. This guy is flogging a microwave oven. This guy here is shaking around some cash. Those are all the goods, right? So these are all the goods we imagine. So these are all part of that D amount of goods. So notice that cash is also a good, right? Okay. Just keep track of how much flows. We keep track of how many bananas flow. And if you look at this picture, it's a big mess, but you'll have to agree that in the end, it's all about how many agents do you have and how many goods and services you have, all right? And for every agent here can possibly, this one appears to be trading, but he could have well be trading with the guy with the turkey or whatever. So you have n times d number of ways these things can combine the different trade, all right? So that's the dimension of this stock space. So we can, here you just see the flow. So they're passing one. This guy is passing, what, 2 bills up and down, right? But there's also a stock space. Presumably this guy has got more than one microwave, at least when somebody purchases it or buys it or exchanges it, right? Their stock goes up. So the amount that everybody owes is here, and the amount that's being exchanged per unit of time is plotted over there. All right? And the dimensions are, of course, the same. Okay, I have these 2 spaces. All right? Now, this is an amorphous mess. All right? So how do we know what the structure of this is? We don't really know. Okay? But we do know 2 things. And there's 2 things we have. The one thing we have is a clock. Right? So this thing is dynamic. That's one thing that's going to differentiate us a lot from economic treatments. They won't consider a clock as being really essential in the analysis. So if you look at an economic textbook, you don't see time really as a variable. A lot of these differential equations is one thing, variable with respect to another. When you take differences or differentials, then they look one step ahead, but there's not this explicit ticking clock that can tick infinitely finely. So you walk around with this stopwatch or this clock in your pocket, and it's right there is the one here, and you can just look at it any time, and you can like stamp in the moment in time that this one is happening, right? So here they're trading this. This is what all that's being passing. This is a big vector V, all right? And we're assuming that everybody has this state here, whatever it is, okay? And the clock struck 11 when that happened, all right? That's something we can measure, all right? What's the other thing we can measure? Well, presumably all these people go back, or somebody is keeping track of this, one of the certainties in life is that you got to pay tax, and in this country you got to pay a value-added tax on every one of these transactions. So you got to keep track of it, and if you don't, the government will do that for you and charge you for this privilege. All right, the privilege of taking your money. So you need to keep track of your stock and how much it's coming in and going out. All right, now for money, bank accounts do this, but you got to keep your inventory stock and down. And how do people do that? Well, they keep their books, you write it down in a book, all right? If it were money, then there are 2 types of statements in this book, okay? Now just imagine they're changing money around, all right? So the one is a balance sheet. So that's on balance, how much do I have in every account, okay? So what I do is for every person and combination of every good that person trades, I open up an account, okay? So each person has D accounts, and all these accounts keep track of those goods for that person, right? Okay? These are sometimes called assets, if you're talking about, if you're an accountant, all right? Either way, what you do is you make this kind of ledger. It's just a big Excel sheet for you guys, now where you say this stuff, so bananas, so many, at this moment of T, right? Moment T in time, okay? It's a big thing. Now, what we would do, we wouldn't do such a thing, all right? We would make a plot, a coordinate system, and instead of making, okay, here's inventory, and here's some capital goods, so this is some inventory, and this microwave is perhaps a capital good, you can use it a lot, you don't have to eat it up in one go, right? We'll make 2, we'll put up a coordinate system like this, and these 2 numbers will be given by a point in this space, okay? But we could have done it differently. We could have traded combinations of bananas with microwaves. Get the free bunch of bananas with a microwave or something. I don't know. And then we would have different accounts, and then you would clock these fruit baskets. So I don't know what you're clocking. All right? Okay? That's a clear thing. And then how much is being traded, you also have to say. Now, what's being traded is in a during a period of time. So an accountant will typically look at a period of a year or a quarter, okay? Because we always look at a period DT, which is shrunk to like infinitesimally small period, and we measure it. All right? This is just because we do it continuous. There's nothing special about it. It's just that as engineers, we have lots of these continuous tools, and there's no reason to junk in. And this is nice drawings, and that's how we sharpened our intuition. All right. But if you don't like it, just switch to delta t is here. Set your delta t. All right. Huh? You know, a way to look at these small dt's is that it's really valid for any finite delta t. That's really how you have to interpret that limit. So you can get any finite one by sorting out what happens in infinitesimally small ones. Okay. So that's, if you look at an income statement, and again, this is for money, you know, there'll be a period for the period of, all right? And what we will do is we'll say, well, how much did he buy? That's an amount DQ. And they'll divide that by how much time passes, you know, and we'll call that Q dot, okay? And that is reported here on an income statement. Here's the Q dot and here's the Q's, huh? All right? Totally different statement. Now, I put in another kind of coordinate charts and I anchored it right on top here, but you don't have to do that. You can just put it right here, you know. Huh? I don't care. Huh? All right? Huh? Okay? So this is what you have to see. So the whole reporting business, that's just showing up with these ledgers, you know, inventory ledgers, this ledgers, that ledgers, big Excel sheets, okay? Now, your typical business person is going to start working with this and massaging that, you know, and they quickly find out that they got Excel references everywhere, going everywhere, and I don't know what, right? So that's the problem, right? How you get out of that horrible mode of doing that. So what you want to do is do calculus, all right? And, you know, so the calculus is all about how to move around this stuff, and then how to integrate DQ, then to get Q and go on, right? So we can use those powerful tools of calculus in order to do that, okay? Now, when we do this calculus, what we don't want is that it depends on the exact way in which you chose these coordinates. That's just a mess, you know? And we all know this mess in engineering. When you start doing something in Cartesian coordinates, and you spend, excuse me, half your dynamics course figuring out what T and B coordinates are, polar coordinates, all this coordinate transformation. It doesn't really add anything to the physical reality that you're modeling, all right? And a good engineer at that level is somebody who knows how to choose the easiest coordinates and then solve the problem so he doesn't get stumped at his exam, okay? So what we want to do is kind of move away from that and start structuring this thing in a way, you know, using the methods of calculus. And that method is called differential geometry. All right, so those are the tools at our disposal to say what's happening here, how we can first structure these spaces, all right, and then figure out what the dynamics on these spaces should be, okay? Now, I warn you that the dynamics on a flat space are not the same as the dynamics on a curved space. And you all know this, okay? So in flat space, we can all do F as m times A, but on curved spaces, we got Coriolis forces, we got this forces, all kinds of stuff comes out of midair, right? If you are more advanced in mechanics, you'll have general relativity, you know, it's gravity coming out of midair, you know, but thin air actually, not even midair, huh? Okay, huh? Nobody really understands it unless you look at the structure of the space. So the point is, the structure of the space is very important to derive the mechanics, okay? All right? So with this lecture and the next one, I want to kind of give you lots of examples where the physics and the mechanics and the geometry that you learn there fits that of the economic problem and get a good intuition for that. And with that intuition, then we'll put the dynamics on top of it. So this is really all about kinematics and putting the dynamics on top. What you really want to do, I misspoke a bit. I should put the kinetics on top of the kinematics, and then I get a fully dynamic model, all right? So first, we're just going to figure out the kinetics. Now, the kinetics in flat space are easy. There's any point and you have a vector, okay? The trouble comes later, all right? And there are several theses where this is just a problem. If you don't take account of that, like your thesis, it's the one I can think of. If you don't take account of it, your numbers are just way off, all right? Okay? So this is a mess. This is what we want to do differential geometry for. This is a clock. We have this clock. These are these reports that you put out. But we want to take a very different attitude towards these reports. We don't want to have Excel sheets. What we want to do is do it all graphically. So we're going to do mortgages. We're going to do annuities. We're going to do all this stuff. And we'll make graphs of the motion in the plane rather than some kind of piece of paper that gives a particular state and another piece of paper that says how this thing is moving. Right? The next state comes, like a balance sheet and an income statement does, you see? So this is an important step, that we first make the reporting geometric rather than, if you just took a regular reports package as you get with SQL Server or something, they'll just put you out these tables, all right? Once in a while a graph, you know. But nobody makes a geometric picture. Well, that's not quite true, but this is where a lot of the power is, because this is how you can picture the kinetics, the dynamics. We want to picture it as living in that space. Okay, otherwise it gets too confusing. Okay? So part of this thing is to see that these accounts, they are the same thing. They're analogous to, I don't know how you would write that like this, to dimensions. So every time you have an account person combination, so someone's account for some good, you have to open up a dimension. Okay? Now here the dimension is something abstract. Here you can give it like an arrow this way, right? This way. So it's a potentially big space. All right? Okay. So here we are. So now how do you picture the interaction of reporting and time with this amorphous set of economic states that, in this case, they're more like the trade, describes what's going on in the trade, you know? So how does time go, you know? How does the reporting go? We want to have a mathematical setup for that, all right? We all feel how it should go, but it's an insight to see that what time really is a function from R, so time is a function from the real line, that's this, here, the timeline, okay, into this tangent bundle, okay? All right, so what does this do, this function? It takes any moment t and it maps it into, well, let's just start with this. It also is that, but that's a lift, all right? Into the configuration space, I want to first go, all right? The multi, and it gives you the Q that you have at that moment t, all right? Okay. So Q initial, say that, gives you, whoop, T initial says, okay, you're there, all right? At T, you go to this Q at T, right? At the final time, you go over there, T final. All right? Okay? So the domain here is this thing, and the image or the range is this path in space, okay? And this path we can think of as the activity or some course of action. I'm using the word course because it's just a Latin for path, all right? And the actions are the trade, huh? Okay, and it's just a nice English word. It rolls off the tongue. So literally is a sort of a path of all the trading activity, huh? It's the path of the trading activity you can view it at, okay? So this is a bit of an insight, right? Once, if somebody just says it, you go, oh, okay. But what you have to do is step back a little bit and say, well, how do I model time, right? What is time, right? And then somebody says, well, it's just a function from the real line into your configuration manifold. So, huh? That's interesting. So I can have another course of action, and then maybe this will be mapped there, this will be mapped there. So he goes, woo, something like that, right? You have all kinds of different courses of action, okay? So I can vary this map. And what my idea is to find some optimal course of action. So my whole trick in this exercise in the end is going to be which map here is going to be the best one, according to me. All right? That's our end point. Okay? It's going to be a busy thing because this is, so you have to find the best among a set of functions, so a set of graphs. You have to find the best one. You can't just take a derivative of something with respect to a graph and set it equal to 0. You can understand that, right? You can take the derivative of a function with respect to some single variable, even if you have multiple, you just have some Jacobian or I don't know what, right? And then set that equal to 0. But you can't do that with a graph. Okay, you got to kind of wiggle it around, huh? And find out, huh? Okay. Okay, so this is the task we have. So you'll see finding this right graph is very dependent on the structure of this manifold here. Let me give you an example just from geometry. Geometry comes from geo, which is a Greek for earth, right? Huh? And metry, which is Greek for how to measure, right? Huh? So it's measuring the earth, all right? But it's used for everything. So you have Euclidean geometry. It's really not measuring the earth. It's just measuring space. But now let's go in a flat space. And I want to find, let's think of this thing as, I want to find, say, the optimal path is the shortest path. Say I want that. I'm light, okay? So that's easy. We all know what that is. That's a straight line, ka-chink, right? Huh? Okay, boom. And a plane, same thing. Free space, same thing, right? Okay, all right. Now I ask you, what on earth, right, is on earth, comma, right? Huh? What is the shortest line between 2 points? Okay. Now, obviously, you can't go straight through because you'll be burrowing through the earth. All right. Huh? So you got to go around the surface of the earth. What's the shortest? It's not so obvious, right? So you'll have to take some kind of derivative with respect to all these best possible ways you can go from place A, say Amsterdam to Boston or something, right? And then you go figure out that you measure, and then they go, oh, this is worse and this is better, huh? So it's a big exercise to do that. And the area they do that in is called the Riemannian geometry, all right? So Riemann was a rather brilliant, in my eyes, mathematician in the 19th century. He was the first to kind of see that, that you can do this kind of minimum path stuff in arbitrary spaces. It doesn't just have to be Euclidean space, all right? Huh? Before that, everybody thought space equals Euclidean space. Every space in 3 dimensions, and it always has a Euclidean metric, and all lines are lines, and the shortest distance, and all parallel lines never meet, and blah, 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 all this stuff, right? And then later, but they knew, of course, with Earth you couldn't do that because they were navigating and they realized they got to go in a whole circle, to get closer to the pole or something, to cut off. So he was the one who extended this idea of finding the best path to the sphere. Huh? Okay. And then this got extended to spheres that are inside out, like negative curvature. Those are hyperbolas, and they get hyperbolic geometry. Huh? And you can have paths there. That's what Einstein or Minkowski used when he interpreted Einstein's theory of relativity, special relativity. And then everybody realized, well, let's generalize this. We can take any space, right? Huh? And we are the inheritors of this generalization. So we can set up an arbitrary space, and in this way set up a way to find the right metric so we can buy the cost optimal path, all right? The most economic path, right? So everyone who's gone before us has given us these tools, but these tools just make use of differential geometry, all right? So perhaps it started with Riemann, but then it was still considered, all right, okay, fine. Huh? I think Gauss tried to measure the curvature of the Earth, but he was, I can't remember, 18th century or something, or end of the 17th. And he just couldn't get an accurate measurement because it was too long ago. They couldn't, huh? But they knew that it was round, of course. Huh? And then with Einstein, everything changed. And everybody realized, okay, the universe is hyperbolic. Yeah, we just have to deal with it. And then it became a big field of study. Okay? And we're going to use these tools. Why? Because in economics, we always want to have cost optimal, or maximal benefits or maximal utility. Something always has to be maximized or minimized. So it's a great setup. Okay? Now, I just defined a path to be this map. But then, if you do that, you can do something that's called a lift. And you lift it into the tangent bundle. Now, this sounds really fancy, but what it is that if you have this map from R into Q, right, and it's continuous and differentiable, you can draw the derivative, the directional velocity at any point, okay? You see that? So you got more information. So I can take, if I can push forward 2 points, I'm pushing these forward into the manifold, here one. So I can push forward a change, okay? Because I'll just do it here, right? And then I can push forward an infinitesimal change, and I'll plop into a higher space, okay? So when I have a path like this, and it's in the parameters by time, I can plot the velocity, which is our quantity demanded, or the amount that gets traded, right? The activity, in its own space, okay? So I can lift this path into the entire cotangent bundle. So not only at this point Q do I know where it is, but I also know this number V, which is an element of the tangent space, okay? And I do that for every point. And that's what we call the lift, okay? All right? So when I look at my economic activity, I'm in this way able to identify, all right, a stock position, right, your inventory, to at the same time, from this course of action comes the amount I'm demanding, I'm trading at this moment. You see, just because I can differentiate along this path. You'll also appreciate that this whole business is independent of what coordinates I took. The path is what it is. As long as it's differentiable, I can bring these things arbitrarily close. I know what units of time I chose, and I just do it. I just define this thing to be the directional derivative and done. All right? I mean, you know it. You can just draw it, right? Without telling me what your coordinate system is, right? Okay? So it's a nice way of looking at it. This is what we call the tangent lift. So the tangent space is the space of the activity, the flows. This is a space of stocks or positions. Yep. All right? Okay? Cool? Yes.
Why is a tangent space not the space of incentives, because these are the incentives at that point, right?
No. So what is this tangent space? The answer is no, right? And there's not an incentive around yet. We don't have this incentive. Okay, I'll give you first the philosophical answer, and then I'll give you the mathematical answer. So what is an incentive? That's a cause for the motion, right? Not a description of the motion. What's a force? A force is a cause for a change in velocity, not the velocity itself, all right? What this thing does, it tells you how your stock level at one moment and another moment, how you can change. So you look at the change in stock level over some time t, right? How is that a force, right? You see?
You could calculate the incentive if you know this change is very big, but you know this person that's
How do you know that?
Because
you could just be going with a very high velocity on the highway and not be, going at constant velocity, and you have no forces. A force causes an acceleration, not a velocity, my dear friend. Huh? So you can go at the speed of light without any forces acting on you. In fact, that's what light does. Okay? Now you're talking about a change in velocity, all right? And then you imagine there a force to be there. So you're going way beyond the kinematics now, right? Huh? But even then, you have to be careful. Like in a flat space, that's okay. If you have a change of velocity, Newton tells you must have a force. But in a curved space, that's certainly not the case. Because suppose I'm on a circle and I'm going at constant speed. Okay, so I'm going here like that, and I'm going here like that, and I'm going here like that. Did my velocity change? For me, no. But if I look at it, it did. It turned 90 degrees. Is there no force acting it? Well, it must be, yeah. But yet again, it's no. Okay? So there are weird forces that depend on the structure of the space. And you'll kind of know this because you have centrifugal forces, you have this forces, you have that forces, huh? Even on Earth we have these, huh? All right, but they are forces that come from the structure of the space, all right? Not the kind of forces that you're imagining, all right? So, number one, you're going way too fast, okay? Huh? You have to first, you see what this is doing. What this picture is doing, we're just trying to describe what they're doing, not why they're doing it, okay? The why will come later, okay? The what, huh? So this is the kinematics, huh? So I can look at the kinematics of a robot hand. I'm not telling you why it's moving like that, what voltage I put on that motor or whatever, right? That actuator, huh? Okay? Huh? I just say, this is the angular velocity, that's fine. And this is the position, that's fine. This is what the thing does, all right? Huh? You see? It's a purely kinematic solution, all right? Huh? Now, these things will tend to go with a constant rate, all right? And then if they don't, you have to add the torques, the incentives, all right? Huh? Okay. Now look at the mathematical answer to your question, huh? It's right here. Suppose I'm here, and then later I'm here, right? So I'm at first I started here, and then later I'm at t plus dt, right? Huh? And what I want to do with this velocity here is I want to subtract these two and divide by dt, right? Huh? How is this an incentive? This is by definition the velocity. You see? The difference in location is divided by the difference in time. You can't call that an incentive, you see? You see? Huh?
But did you mean that if you know the curvature and you observe its motion at every time, then you can infer.
Yeah.
How do you infer that? How do you infer that? What structure is here that you can infer that?
No, if you know the structure, like if you know that at every point.
No. You still need a Lagrangian, you still need a Hamiltonian, you know, huh? Okay, huh?
This tangent space consists of all these.
What?
The tangent space consists of at every point in your course of action
Yeah.
of this V, right?
Yeah.
If you know the entire structure and you see the V is changing, you must know that the V must change due to.
Well, here you see a V changing, but it doesn't change.
Yeah.
Okay.
But then there you don't.
Well, whatever you see, you'll see no. The answer is just no. All right. Huh?
Tangent space is also every possible velocity that could be. So you have very limited information from there.
Yeah, but he's looking at a particular path, particular tangent left, and he says he can deduce the forces from that, the incentives. And I say, no, you can't. You'll have to tell me, you first have to define what it is, a force. You know, we haven't done that yet. All right, before you do that, you have to define first what the momentum is. We haven't done that yet either. So in order to define momentum, I have to give you a Lagrangian, and you have to take the partial derivative and call that a momentum. And then I have to have the cotangent bundle, and I have to do this, and I have to do that, and I have to be such, and I'll do it so, and I have to take a path in the cotangent bundle, and then finally I can get that F is speed up, and I have the Euler-Lagrange equation, which was the whole final result. And what you're doing is you're taking this final result, the Euler-Lagrange equation for the simple case, which is a flat surface, and then endowing this whole thing with that one little tiny result. And it's just a path that's going to lead you to all kinds of misery, right? So what you need to do is unravel everything you know and realize that what we're doing is we're starting from scratch. And we're building things up one piece at a time, okay? So the way Newton did his Newtonian mechanics, he just threw everything on the table at once, and he says, okay, this works. The way this works is you start from scratch, and slowly you start adding stuff, okay? So first step is to make, to describe the space, okay? That's all. Then a second step is to add the dynamics. So I have to add the action, some costs, and then so I can look at marginal costs for the price. And then I have to look at the structure of that thing. And then I have to throw a principle in, which is Hamilton's principle, right? Huh? So some way of determining what the optimal path is, some differential equation that does that. That is the Euler-Lagrange equation, all right? Huh? And blah, 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 blah. You can't take shortcuts, you see? Huh? All right? Okay? Clear? Even you won't fix it. Huh? No, because the Euler-Lagrange equation can be quite complicated. If you look at electrodynamics, you can't just say F is P dot. Huh? Okay. Well, first of all, what is F and what is P is very complicated. So if you have a rotational body and then all of a sudden the P becomes angular momentum, sometimes, huh? And then it doesn't, F is not P dot. Well, it is if you interpret it right, but you see a tennis racket. Have you thrown up a tennis racket up in the air?
No, but I can imagine what that was.
Yeah, well, throw your cell phone up in the air, do it on a concrete floor, So, huh? How does this thing move? It will do really weird things. Is that because there are forces acting on it? No, obviously not. It's just free motion, right? Yeah, a little bit of gravity, but ignore that. All right? Huh? You'll see it makes all these, huh? Is it because the forces acting on it? No. Huh? No, that's just the way the equations of motions are, because the inertial, the inertial tensor is not symmetric, right? You have an asymmetric object, and it's going to try to flip from an unstable moment to a stable one, and a little bit of friction is going to flip over there. Well, whatever, right? Huh? And you tell me you can see that the forces are acting on it? Huh? You're from aerospace, you will see some satellite tumbling in space, It's doing that without any forces. It's making very complicated motions. Huh? All right? Huh? This is just not because that was a dumb thing to say, but it took people a long time to realize it's just wrong, And we have to set this up slowly but surely. All right? and then find out what's wrong. Because how do you explain this motion? Even if I throw this pen in the air, I mean, what is it going to do? Right? Huh? Only when you throw a ball in the air is it going to look easy. Huh? Yeah. Let's go. Okay. Huh? This thing is not going to look so easy. Oh, that laptop of yours. Or even yourself. if somebody throws you. Put your hand up. Okay. All right. So here I told you this is the lift. This thing is the lift. And how do you interpret that lift in economics? Economists will talk of stock flow consistency. Okay. So this is a new idea. Traditional economics doesn't contain that. Traditional economics actually only looks at these flows. All right. Huh? So if you look at the, Marshall's work, the quantity demanded for oil, what's the demand for oil? They will always have a flow variable, now so many barrels per day, and then they have a price, right? Huh? And the fact that you may have some huge storage, but you don't want to buy anything, they don't look at, right? Huh? So they're only in this tangent space, okay? Then some things in economics are in the stock space, like capital goods, I believe. They look at they call that stock variables, and the other ones are flow variables, all right? So they have two types of variables. Those who live in the stock space are very few, right? The money supply is one, I believe. Huh? I don't really know. Huh? And then those, which is all of the others, living in this only in the tangent space, or what we may call the flow space. Huh? Okay. All right. There's a small danger of confusion here because for us, especially with bond graphs, a flow is this vector, right? There's a flow vector. But for a mathematician, the flow is when you add all these vectors together and you solve that, and but I wouldn't worry too much about it. I'll just mention it. Okay. So when I say flow, I mean a flow vector. All right. Okay. So what we will have, and then later on they started talking about keeping these things consistent. So if there are certain flows, they have to flow to somewhere. See, the early economists, when they just looked at demand for oil, you demanded all this oil, but then what you did with it, they didn't even look at it. They just said, okay, you have a demand line for oil, right? Or, hey? All right. And then later they started building these models, and for especially on computers, and then they say, well, we have the storage now, right? With this system dynamics models, system dynamics models. They have these stores, and they want to enforce stock flow consistency. Also in these DSGE models, I believe. Huh? I'm not so well versed at when they actually start doing this, but the way we would say it is that this path is the tangent lift, right? So you define the velocity in this way, right? Basically, okay? As the directional derivative, all right? So the size, the length, the magnitude gives you how fast you're going, and the direction tells you, the mix of goods you're doing, okay? Notice that this is a vector space. Why? Because it has a point of 0 right here. So you can add two vectors, you just, in this way. All right? Okay? Because the 0 demand is clear. This is when your stock is not changing, right? This thing is not a vector space. Well, first of all, it looks curved, so it can't be. But even if it is not, what's the point of 0? Nobody knows, okay? You just take an arbitrary point. There's no natural 0, right, to begin with, all right? Okay. There are several other reasons, okay? You look confused about that, All right, now I'll deconfuse you in two ways. Suppose that the stock space is a circle like this. So this is just a pendulum.
Mm-hmm.
What's this? Is that a vector space? Where's the 0? A vector space needs a 0. Where's the 0? Even King Arthur can tell you that now. I think he'll make the same joke yesterday. See you?
Yeah.
Okay. All right. Now suppose you just here, this space position. Where's the 0? Okay. All right. Is this 0 or is this 0? You don't know. But am I going with velocity 0 with respect to you? Certainly. Okay. Do I have position 0 with respect to you? Who cares? I mean, you could be at 5. I mean, huh? All right. So, huh? As huh?
Mathematically, it makes a lot of sense. Like even for the Earth, like where would you say the origin on the surface of the Earth is, or any like, yeah, any manifold? It makes sense to me that it wouldn't have an origin. But let's take the example of this space in this room. Like, yeah, okay, there's no point that I would call the origin. But if I'm counting how many people are in the room, then I would say, well, the door is like. So I think maybe, like in some situations, but I guess you wouldn't disagree with this necessarily. Some situations, the way you make your accounts, where you define to count up and down, matters to you, matters for your books, like for your accounting. But you're saying it doesn't matter for the like underlying, like it doesn't relevant.
No, okay, but I see what you're saying, and even there's an answer to that, right? Huh? So you're going, you're a clever guy, but you're going the wrong way. So what happens in the case you do, is the number of people in this room, is that the manifold looks like this. There's an edge, right? Huh? It can't be less than 0, right? Huh? Number of people. But suppose, so you could say, I'll call this 0, and I'll just add positive numbers, because that's how I decided to count. Right? But suppose I'm looking at the total number of people in the building, and I'm adding to it the total number of people in this room. So say there are 250 people in the building, then this will be 250. You see? It's just your choice to take the lowest point and call that 0.
Yeah.
All right?
Yeah.
And it's not a natural choice. You could have taken 250. But with a vector, it is a natural choice. You have no other option, right? Okay? Another way to see it, I mean, when do you need the number 0 anyway, right? The Greeks didn't have 0, right? The ancient Greeks, so they were doing great counting, right? When do you need the number 0 anyway? Well, you need it when here's a positive number plus 1 when you introduce negative numbers, right? So what's a negative number? Now, how can you have negative number of people in this room, right? That's just stupid. Right? Right? Huh? Okay. Well, you could, because say, well, we're looking at an average, and then does this room, is it below average or above average? Now, all of a sudden, it does make sense, right? It's not so stupid, right? Huh? Okay. Huh? But then we're using numbers in a different way. We're using numbers to measure things, okay? And that's metric and that's geometry, right? So suppose I'm standing here, huh? And I'm looking at going this way or that way. Then this is 180 degrees and making a turn of 180 degrees, or looking at a mirror actually, right? Because I don't want to turn, because I don't have the space. I put a mirror there. Then I'm going to call everything on the other side of the looking glass, I'm going to call negative. Then I have to call the looking glass itself 0, because it's the only one where plus 0 equal minus 0. So I'm a bit stuck when I set it up like that, okay? Huh? All right, but then you're getting closer to something real. All right, huh? But really what I should be doing is viewing this as a vector space and adding something, because I'm taking a step. And then I'm really not in the stock space, but I was in a vector space. And I just ended up integrating it out. Okay? All right? So the sad fact is that positions are just labels. All right? But they're more than labels. They can be arbitrarily close. Okay, and number of people in a room not. You can't have 1.1 person, right? Huh? Okay. All right. Huh? Have I convinced you guys? Huh?
Yeah.
Huh?
Yeah. I'm waiting for the examples to see it.
Yeah, you gotta stop asking good questions. Huh? All right. So this is stock flow consistency. All right. Huh? Okay. Oop. Now, because I like these questions, I take a little bit longer to do it because there are so many misconceptions building ahead because you've taken too many courses and passed too many exams. You have to kind of unravel that in order to go back to the basics and clean up your mind. Otherwise, you fail at this kind of stuff. All right. It was a long ride for me, and therefore I want to. Huh? Okay. So now I want to start at the simplest of all spaces. Okay, the ones you are completely familiar with, and then work this out. And the way I view it is that only commodities, and that's precisely what that paper Newtonian mechanics was about. It didn't say goods or services, okay? Goods and services are, in general, way more complicated. They're not in a flat space, all right? But commodities are. They're fungible. You can't see the difference. You're infinitely divisible. I don't know how they define that, but you can buy them in fractions. They talk about fungible, so you can't see the difference, right? Which is important because if you have a dimension like that, you're just assuming that you can switch this unit over there, right? Space is fungible, right? You can take this piece and put it over here. You will never know, okay? Huh? All right? If you have pieces of fine art, that's obviously not what they call fungible, right? You would say exchangeable or something, but the fungible is the word. Huh? All right? So you know all the definition. So suppose we'll have one degree of freedom, okay? Huh? One agent with one commodity, all right? Huh? It's a little bit of a silly economic problem for trade, but whatever, huh? Okay? Huh? I just think of him magically getting stuff from God or something, some paradise or whatever. Huh? Apples that are just there. All right, so he's just getting apples in paradise, this guy. Huh? All right. Then what is the configuration manifold? All right, well, that's just this line. Huh? And he has, Adam has Q apples. All right now, okay? And what is the tangent space? Well, that's the number of apples that he is receiving. Suppose he receives one apple at this moment, and then this will be, the rate at which he's receiving apples, okay? Now, normally what we do is when we have that, we'll just draw this arrow right on top of that, right? But that makes no sense because these are like, I don't know, 10, 20. Now this thing is not 20, it's 20 per second or something. So you can't really do that. We do it, but in our mind, we really have a different space. It's like right on top of it where these are in units per time, second, I don't care, or year. Huh? And these are these items, huh? Okay? Huh? So they're different spaces, okay? All right, huh? You see that? And that's what you see over here. So over here, what I did was I plotted it right on top. Now I do what we normally do as engineers. I take this tangent space, okay, this flow space, here's the Stark space. I'll just draw that normally as a coordinate, okay? Huh? Here it's not a coordinate, whatever, right? Huh? And then this tangent space, I'll just flip it around. What does it matter, right? I could have put it over here. As long as I know that it belongs to this point. That's all I need to know, right? Okay? Huh? So what you do is you put it over here. Now, if I were a point further, say here, then I would have another tangent space with another vector. Maybe he's getting more apples. So that will be over here. I'll have another line, and then there will be some point over here, right? Huh? You see that? Okay. This is what we normally call the state space. Okay. So it's 2, and we will write it like this. All right. So we think of this thing as orthogonal. It's not orthogonal. I mean, if anything, it's parallel, right? Huh? Okay. Huh? But we just plot it like that as engineers. And then we think of this as a vector in this space. But you really shouldn't, right? Because if you do that, then this will be this vector, huh? Because this is q dot, huh? Here's the 0, then some arbitrary 0 that I took, right? Here's q. Well, what's the point of this? I mean, what's this angle? There's no angle. It doesn't exist, right? Huh? What's the length of this thing? This velocity squared plus position squared. Apples and oranges? No, no, no. So, you know, so it really is a little bit confusing to do it that way, to call this a vector, because it's not a vector. Okay, it's just a column of numbers. All right? Huh? Okay. You're not convinced of that, right? Huh?
No, I am.
Hey, you see? Because you were shaking your head. Huh?
Yeah, it makes sense.
Huh? You see? Huh? Or you're shaking your head like, no, it didn't make sense what I learned before. Right? Huh?
Because basically just a system of equations, and we call that a vector.
Yeah.
It's just a system of equations.
Yeah. We call it a vector. It is, you can call this a vector if you want, and some mathematicians do that. But for us, it's not a vector in the sense of an arrow, right? That you can just draw as coordinate independent. This thing is totally coordinate dependent. It also has no inner product with another one, right? There is no magnitude, there is no nothing. It's just really a column. You're allowed to call it a vector, but be careful. Huh? All right? Huh? And it does live in some abstract vector space, which is not a Euclidean space. That means there's no notion of angle. So it is in some weird Hilbert space. Huh? That's what they call a Hilbert space. Well, no, a Hilbert space is already more. So worse. It's like not even that, right? Huh? But you know, huh? It's like what we really should, what this is known as is a fiber bundle, huh? I guess it's American English. You would write fiber like this. I never know. Fiber bundle, huh? Why? Because there's you think of this as a fiber, right? So it's like a piece of cloth, right? So you have your thread here, and at this point you just put these fibers in, right? Huh? Or like a piece of wood is better, right? So it's like a tree, huh? So these fibers, they're all right next to each other. Okay, not necessarily with a lot of glue in between. All right. Well, sometimes yeah, because you can move up, huh, a little bit, you know, huh, differentially, huh. Okay. All right, huh. Okay. That's why it's called a fiber bundle. You'll see that notation in geometry. So again, it's a flat space, but it's not a Euclidean space. Euclidean space means you can measure distance and do angles, and you know what parallel lines are. Parallel, whatever. What is crossing? I mean, who cares? Huh? As long as you keep track that this point belongs to this other Stark level here. Okay, that's all you need to do. All right, this is what they call the natural projection map. All right, huh? Okay. And then what we do is we say, all right, you know, we got the state. This is what we call the state. And we want to see how this thing moves in the state space. So here, let's put an A matrix in front of it. And then, you know, a change in this space will be Q dot and Q double dot over here, right? Huh? And then we sort this all out. And then the question is, what is this A matrix? No idea, of course. But on your exam, they'll give you something that somebody derives, you know. Huh? Okay. Now we also want to get this to this equation, right? Huh? Okay. Huh? Well, we're going to have to take some time because this equation is really hard. You know that. Finding the right A matrix is hard. That's finding the whole system. All right. It's not a question of just F is M times A-ing it and saying, okay, I saw the velocity. Now I know. Huh? See? Huh? Okay. So now, if you have two dimensions, this is how it looks. Okay. Now you know two dimensions too. You have Q1, Q2, and what will you do? You have Q1 dot and Q2 dot, and you'll have some, you know. Huh? So what do you have? Here are your Qs. Huh? This is your Q somewhere here. Huh? Huh? Now it's a four-dimensional space, so I can't draw that, right? Huh? You'll realize that I can't draw something four-dimensional in three dimensions, I hope. But I've tried here to indicate that what you really need to draw is at every point here, you need to draw a plane. And I kind of drew it orthogonal. Here it lies on top of it. So I tried to imitate this business. Okay? Huh? All right? Okay? Now, what does the economist or accountant do? He just keeps track of it separately. So he has a balance sheet for this, and then he has a separate income statement for that. And then this is at T, right? Boom. And then he has to associate that one in the books together, and he submits that. Now, next year, he makes another one, boom, and then he has to have a new one, right? And then, a huge stack, and these are called the books, right? So all these papers put together, all right? Clear? So this is commodities. So commodities is just this flat space kind of world, but then kind of done right. So I want you to appreciate that already it's telling you a lot of things you hadn't thought about, right? I'm seeing you with your eyes open, right? Like, and going like, okay, it's already quite enlightening to unravel all this stuff and say, okay, this is what's going on, right? Okay. So a dynamic system does that. Okay. Are we cool? That's commodities. You were excited about the applications. This was your first application. You already learned something, right? Now we'll go to another one. So here I just threw in another apparently flat one, but it's just, I'll go through it. It's going to take a while. This is, Berend did this. Berend Menkveld. For his, he did it for his literature review and ended up not making it into his thesis. But he was working together with Rabobank, and at Rabobank, they have this problem that people have 3 types of accounts, okay? Well, they don't have this problem. They have a situation where people have 3 types of accounts. They have a savings account, and the balance in that account is XSA. They have a time deposit account. You guys know what that is. They have a savings account, you get interest. Time deposit, you can't pull it out until this moment in time. And current account, you can just, just pay out of it, whatever. And there's a certain amount of funds people put in the banks. And what they do is the bank allows you to switch between these accounts. So if you open your bank app, you'll see the 3 of them, and you can move money in between them, okay? So what you have a certain amount of money. These are the funds that have at your disposal, and you can move them around between these accounts, all right? So what are the possible states? Now, this is not a possible state, okay? Right? So all the possible states are on this simplex here. It's called a simplex. It's just a triangle in n dimensions, okay? Let's quickly realize. Here he has everything in his current account, here everything in his savings, here this, and here are all these combinations. Okay? Okay? That's your manifold. This is just the abstract description of this manifold. Okay? As a submanifold of some other space. So this is also what we call a holonomic constraint. Okay? I probably could have So this is the holonomic constraint here. Okay, so we have to say the sum of these two are a constant. That puts this constraint. We call it holonomic because it involves only the stock levels. Okay, only positions, no velocities. All right, okay, it's just a name. Now, when you have a holonomic constraint, you typically get a nice submanifold like this. Okay, this one is 2-dimensional, right? 2 degrees of freedom. And your ambient space is 3DOM. Okay? It's a very typical setup. All right? So then your tangent space also has this kind of, you just differentiate this. So what's this R? I chose R for radius, but it's just a geometric description of this situation. They didn't have this geometric description, by the way. They have big tables and text and all of this, but this description of this sounds all right. This is the manifold you're on, right? And this, any velocity, like here is a velocity, so this is the flow, this is the rate at which he's transferring, right, between his accounts. They have to abide by this equation because I just differentiated this, all right? And this is the total number of funds, huh? Okay, it's sort of a radius, right? Huh? Okay, so this is like a circle, now, like here's a circle, but it's not really, it's more like a, huh? Spaces like this are called L2 spaces. These ones are called L1 spaces. Maybe you've seen that, huh? Okay. So here the radius is a sum of squared. Here the radius is just a sum. Okay. Absolute values, but we're only looking at this piece. Okay. So your total amount of funds, your capital, is this R, and you're defining this thing through this set of equations. Okay. Now you're asking, so here I put this color triangle. You guys know what that is, a color triangle. So you can make every color, now by putting green here, red there, and blue there. There's RGB. And the space of all possible colors is the same space as this. So that's an interesting thing of manifolds. We say that these are diffeomorphic, and in fact, they're homeomorphic under certain group actions. We'll see this later, right? So a problem in banking becomes the same as a problem in, exactly the same. So you can color code the, you could have a coordinate system where the color coding tells you this is what the mix is of the accounts. Huh? So here I took green to be time deposits. Well, it's not so bad, actually. Maybe I should have, I don't know. Maybe current account should have been green. Huh? Or green is because you make most money, but you have most risk. I don't know. Huh? Whatever. Huh? See? Now, that's something, if you didn't take the manifold perspective, you wouldn't really have ever thought of that, right? Huh? But it does say that all kinds of math developed for this you can use to analyze these kind of spaces. Now, obviously, this is also, it looks like a regular Euclidean space, but it certainly isn't, because if you're here, you definitely cannot go this way, right? You're at an edge, huh? Huh? So this thing is putting a severe constraint on what you can do. Right? All right? Okay. So there's a lot of geometry in this space already. Okay. Now, how do you plot coordinates? Now, there are several coordinate systems out there. This is sometimes called an affine space, by the way. It's sometimes called projective geometry. So how to see that? Let me take these two, plot them here, and then this, like that. So I'm just taking this plane here, all right? And I put it like that for a moment. Then a point on here would be, so I have just two accounts. It's a simplex in 1D. This will be a valid thing. But if I look at this space, this whole line is actually all, possible combinations that will have the same composition, right? Huh? You see? Yeah, because they all have the same relative fractions of the counts, okay? So any point on this line you can project down to this point, okay? Huh? And you get the right point, all right? Huh? I agree that you had more funds here, but we're now just comparing different compositions, okay? This is why this is sometimes called a projective space, because you're projecting all points along a line. This is a very natural thing to do because this is what our eye does, right? So if I look at something, so if I take a camera, some of you do this all the time, and you make a picture of something, what really happens is, or you make a painting, your eye sends out these light beams, right? Or it doesn't send them out, receives them, right? Coming into your eye. So here's your eye, right? And then here's the canvas, and a point here gets projected on there, a point there gets projected on there. Now it doesn't really matter how far the point is. You will see them all, now lined up like the star. If you look out at the stars in the heaven, it's like that, right? Huh? You don't see how far the star is. You just see a big one or a small one, and you don't know if it's big and far away or small. Huh? And that's called perspective. Okay, so it's the perspective you have on it. It's called projective geometry. So it's a type of geometry where you look at projections. And that was derived from perspective. It was developed by a Renaissance artist in, I think, the 15th century, maybe a little earlier. I think it's 15th century. Brunelleschi and those people, when they finally figured out, Vermeer here was a student of this. So you see, he figured out exactly how these projections go, right? So he would have made a big thing with a small hole and look at his eye, and then, if you go to that Vermeer Center, they will explain to you, all right? So these kind of spaces have a very interesting geometry, all right? And they're going to have very interesting groups and all of this, okay? A lot of math we can use. Now, in order to keep track of this, we need a set of coordinates. And what these guys use is these relative fractions. And that's just coordinates. So there are 3 coordinates, so it's kind of over-dimensioned, but it's called barycentric coordinates, okay? So you use 3 coordinates for a 2-dimensional space. But these are defined, so you just look at the proportion, so you have this one equation. There's another set of coordinates, affine equations. You just take 2 accounts, and you know that the rest is in the other account, okay? Those are called affine coordinates, okay?
So kind of looks similar to what they use for like portfolio optimization, where you've got a vector of weights, which must sum to 1 method, right?
That's right.
So
you do these weights times, what you do is you take the sum of the weight times the total amount, and you sum that to whatever, right? It's also called homogeneous coordinates or projective coordinates. Exactly.
is that also similar to barycentric?
Yeah. Whether this is a portfolio of stocks or accounts, what does it matter? All right? Every time you have a portfolio of a composition of something, and you look at the composition, use homogeneous coordinates. They're called homogeneous coordinates, And then you are in a projective space. You're in now, That's right. It's all the same. That's a good point. It's all the same. They're all the same. Very general setup. I mean, how can it be the same as a color, right? Okay.
Yeah, colors, of course, nice because you've got 3 dimensions now, so you can easily map it with. If it's higher dimensional, it's much more difficult to visualize.
Yeah, of course. But you can do it. In robotics, they use them all the time, right? Homogeneous coordinates and Euclidean motion, you do it. It's used, painting. Cameras, these vision guys use it. That's right. So for portfolios, that's the way to do it. That's right. So this is just a portfolio of bank accounts.
But that's a sort of property of this type of constraint that we got lucky with it, and now we have like a 2-dimensional space instead of 3, which would have been much tougher, right? That's what.
Well, you have to look at it different. Not so much you get lucky. What you do is you go to a big space and you look at the constraints you have and you build those in.
Yeah.
You see?
But those constraints that were in this case were such that.
Oh, so yeah.
Nice.
That's right.
Could be that you get like.
Yeah, mess. Yeah, sure. Yeah, but okay. So my position is, I want to give you examples of things that work and show that there is a large amount of it, right? You know what I'm saying? You're totally right. Most of the time you'll get trash, okay? But then you realize that the annuities, I'll show you in a bit. You get a real annuity, you get all kinds of junk. It's non-holonomic, okay? You can have non-holonomic constraints. You can roll a coin, it really sucks. But annuities, you can wiggle them a little bit so they become holonomic and then become easy to model, okay? With exponential growth, it becomes another holonomic constraint, you'll see, Okay, capital theory, you can wiggle them so that you always get a nice. So even if it's a mess, you can see, well, how do we demess this? And then often you're close enough, and then you can see other things as, So this is the trick in Lagrangian mechanics. You see, this is what's wrong with Newtonian mechanics. So suppose you're doing Newtonian mechanics in this space. You have no choice but to have three forces, three incentives, okay? And then you start calculating like a maniac, and you have to build in all these constraints all the time. Super complicated calculation, all right? It's comparable to when you have a pendulum, right? Huh? Sure, you can have these forces acting on it, but it will be awful, right? Because you're better off just getting a torque, and then you're done, all right? Huh? Now, what Lagrangian mechanics does, it first realizes, look at Newtonian, you later on build in that you're in this submanifold. You first set the whole thing up as if you're in this humongous space, right? Huh? That's what you might do with portfolio management too. You know, in humongous space, and then you start saying later, after I've done that, okay, well, I have this constraint, and you put it in. Well, the trick here is to first put in all these constraints, so they're on your submanifold, and then figure out what the dynamics is, you see? That's the trick. Same trick Einstein did with gravity. How can you figure it out? There's this Newtonian space, and where's this gravity coming from? It's thin air. And then how do you see the difference with a guy in an elevator and gravity? You can't even figure it out. So he changes the space he's in, and then all of a sudden he's able to do it. Okay, just set up one principle. The equation is a little bit long, but not too, okay, you see?
The constraints to reduce the dimensionality of your problem.
Exactly. And then, only then, do you set up the kinetics. Then you figure out what the dynamics is on the new constraint space. Okay? That's the trick. So you reduce not only the stuff you have to keep track of, okay, but also the incentives and the prices you need to keep track of. All right? All right? Okay? So that brings us to our next example, which is capital theory, because capital theory works like this. Is sort of a capital theory, right? You have a total amount of capital. Those are the funds available, right? And that's a constraint. A budget constraint is another constraint. However, it's often interpreted as non-holonomic because the budget is a flow. You get so much money per year. So it will be constrained on the tangents, but we don't want to deal with that right now. Let's just first do the holonomic ones because they really reduce the system, all right? So to talk with you, Andre, let's first see if we get lucky, all right? That's always a good approach. First see if we can get lucky, and then if we don't get lucky, then we'll have to do the work, all right? So it's true we were lucky, but let's first see whether we can get lucky, all right? And even if we don't get lucky, we look at it, and we say, well, what if I do some small things here that the customer won't mind or whatever won't mind, and now I'm lucky, right? And I'll say, I'll make some approximations, but then, okay.
Control of our own destiny.
That's right. You can force the luck. Once you know what it is, just put yourself in the way. Usually, that's the only way you can force luck. Is luck it will come when you put yourself in its way. All right. Okay. So this is an interesting thing, and it leads us to the. So I'm not regretting. Why am I making this now? I'm not regretting going slow on this. Because I see you guys. Now here, I wanted to unravel this and do it one by one, and I ended up not having enough time. So, and unfortunately, I'm running out of time here too. So I'm going to give you the overview of this, and the next time I'm really going to get this one home, because this is a great example. And it will bring us very far. It will tell us how to generalize more generally and how to use what is called the exponential map So we can take the notion of exponential growth and the rates of return and exponential growth and generalize it beyond anybody's imagination. All right, so use that same mathematics. And the magic that's going to make that work is group theory, and us being able, to view these sub-manageable not just as a bunch of holonomic constraints and here it is, but as part of a bigger way, the higher, more abstract machinery under which this not only works, but also gives you all kinds of other structures very compatible with economic thinking, okay? I would say especially at this kinematic stage with the exponential map. And your model, somebody just posits exponential growth. Where does that come from? Well, that may come just from the shape of the manifold, okay? That's the thing to see, all right? Huh? But exponential growth is just growth, but you can have all kinds of weird exponentials, and you kind of know this because when you look at Euler's theorem on a circle, that's also an exponential. It's just got this little I there, right? Huh? Okay, and this movement we can see as an exponential. And you have quaternions, they describe things in 3 dimensions, 3-dimensional manifolds, also an exponential. And the exponential map is just this phenomenal thing, okay? And that is going to be kind of my endpoint for the kinematic part of it, okay? So we're in really good shape and see why we really need these manifolds, okay? Huh? And why just going through Newtonian coordinates is the last thing we want to do, huh? Because we lost everything that we tried to gain. So I'm going to make the first stab at this, just to, again, so going back to the theme we had laid out before, that what we want to do is get all these ledgers and Excel sheets and everything into more of a coordinate representation, right? Graphically, be able to do it as trajectories and those kind of things, right? Coordinate systems. That's the way we can do it. So I'm going to start off this very simple example and then build it out, all right? And in this simple example, and it's actually not so simple, I already got 3 kind of motions. One is I call production, the other one I call growth, and I call this amortization, all right? And again, we have an ambient space of 2 dimensions, one that I call capital, some generic form of capital, and one that I call the product, all right? It's just 2 goods. But what happens in the economic reality, the trade happens only in a configuration space of 1 dimension, all right? Although there are 2 goods involved here, all right? And the reason I have these together, all right? So what does that mean? That means I can map the configuration spaces into this real line here, okay? Right? Some business person may give me a single Excel sheet with this. And I already suggestively named this the return, and this is my Q, is a return. Yeah, normally maybe we'll, okay? It's a return, all right? Okay? Now, how do I do this? What I want to do is start with this green one. That's the simplest one. And then assume that this is a plot of land, what you have. So many hectares, okay? Now you're a farmer. You're going way back. 10,000 years ago, this was the only form of capital available, right? Even you yourself is not a form of capital yet, because I don't think they had slavery yet, all right? Okay. And then what can you do with this land? Why is this land useful? Before they invented farming, this land was useful, but not something you would pay money for or be willing to defend. Why? You would just go with your little band of brothers and sisters and scoot around and you gather something and you shoot at something and eat it, and then once in a while you meet some other tribe and you say hi, maybe somebody has a disagreement and go point, but there's no war, there's no trade, there's no nothing. Everybody is kind of more like animals would do now. They just forage and hunt, okay? And they do this in little tribes that they move around. You see, I think there's several places on Earth, like Mongolia is one of the few. I went there. You still see this lifestyle. They have tents, and they just move around. Okay. And then something happens, and now you have this land here. Okay. Now, land is what they call a fixed resource. So it doesn't change. It doesn't get more of it, no less of it, you know. Whereas assuming you can't conquer land. You could, and then you're out here, right? But it's not something that grows, okay? And what you figured out is that on this land, you can grow this kind of grass that has a big like kernel, right? And you can go eat these kernels, okay? Or you can trade them and give them to somebody else, all right? So that's your product. So that's your oogst, harvest, huh? Also called the yield of the land. That's what, it's what the land yields, literally, all right? It's not the land itself, it's what it yields, okay? Right? So you have two different types of goods. You got capital goods, which is this land, which you can't do anything with. The only reason they have some type of value and will have some kind of dynamics on it is because you can get a product from it. Okay? Right? Yeah. Okay. This setup has been used much later in all kinds of other forms. So, especially in the Industrial Revolution, you'll see that, well, later then labor became also a resource, you know, like this, capital resource. Even later, ships came in the 18th century. You know, you will have a fleet of ships going through the east or something, and they became a valuable resource. The ship itself you didn't care about, you know. You cared about the cargo that's in the ship, all right? Huh? In the Industrial Revolution, this went nuts, okay? And new forms of capital were invented, okay? Huh? And then this blew up, and all kinds of new products came, and that gives us a much larger space to deal with than primitive man, who was in this way smaller space, you know, where there was just land, and they didn't need economics. You just have one fixed asset or resource, and then you have one or two products, okay? Huh? Okay? Well, there it was a little bit more complicated because of all this harvest, you could like have some people, you know, differential land, so you gave them some free food, but they needed also the capital, that was their knives, and they were sharpening it, you know. Then you needed another guy in a city to make a pot and a pan, and he had his tools and his capital, so it got a little bit more complicated. So if you look at Roman society or even Sumerians, they did have this kind of artisanal industry going as well. But the big forms of capital only came in during the Industrial Revolution, right? 19th century, end of the 18th century. Okay? So let's fix your land. And it's an interesting theory that was put forward by Ricardo, because this was a question that was unanswered in regular economics. So why does land have value, right? There's no demand line, there's no, but you know, huh? You don't see it now being produced. Huh? And Ricardo, he answered that. He says it all depends on, the value comes from the product, okay, of the land, you know. And the fertile land is where this product is high and infertile. So we'll be able to do the dynamics of this in a little later. But in order to do that right, we now have to set up the kinematics. All right, so there's something going on here. And there's something a lot deeper that's much part of the history of economics. And I would even say if you just had commodities, you don't really need economics. You just exchange these commodities like these people are doing there, right? I mean, what's the problem? I have some berries and you have some meat here, cha. Huh? You know, we don't need our money. Huh? All right, huh? Okay, so let's start with this thing. So if R is constant, so this amount of capital, this land is equal to R, so I'm calling this R as a radius again, then it's obvious to you that you're going to be on this green submanifold, right? Huh? This is what your space is. Now you could index that by the total amount of seeds or whatever you're getting out of here. Right? Huh? And that will be this This will be this. You would measure this in seeds or something, and this will be seeds, okay? But that's not what people do. What people do is they say they want to know how fertile, how much, they would divide these amount of seeds by the size of the land, right? Number of hectares, all right? And then you get this ratio that's called the yield, right? So many seeds per hectare, okay? It's way more interesting, okay? Now let's look at that. So suppose I look at the seed velocity, and I divide that by the number of hectares, so there will be this vector, and I divide it by that. How would you call that? If you divide this velocity here, v, by this radius, what?
Angular velocity.
Yeah. Okay, now that's angular velocity, and I integrate it out. What is q divided by r? Because r is a constant, I pull it out of the integration. It will be the angle, right? Okay. That's a way better way of describing this point, is by giving this angle. That's what we did with these barocentric coordinates as well. All right, so we give this angle, and it corresponds to the return. In this case, that's the same as the yield. All right, as a percentage. No, not a percentage, because there's a seed per hectare. People don't like that. You know what they do? They have something they call the reseed ratio. And they turn these hectares in terms of seeds that are equivalent to what they need in order to seed that land. And then you get a measure for the size of the land. And then this thing becomes dimensionless, okay? And then you measure it in percents, all right? Okay? That's what happens. And that's what they call the yield. And the velocity is the angular velocity, is the yield rate. Okay? So here's something nice happened, that Andre, particularly, you should be happy with. This is a picture of a rate of return that's completely geometrical, and that C looks at the return as an angle. All right? This would be very satisfying. It does the same units. And now I'm doing geometry all of a sudden. I'm just not keeping track of numbers in an Excel sheet, okay? Because of course the dynamics is going to be, okay, how do I change this, the angular velocity? Well, I'll need a torque, so we'll have to figure out what that is. Well, come later, later. Okay, okay, guys, all right. I'll give you another example. So this is the oldest one. You go to your bank and you plop something in your current account. Now, these current accounts, I don't think they give any interest, right? Do they? No. But if they do, they plop it in an account that pays you something called simple interest, okay? You know what that is, simple interest? Your money just gets interest, but you can't compound it. You can't leave it in. They'll just pay it out, okay? It's like a dividend in a stock. So this is a stock you get your dividend by, or a coupon on a bond. You just get paid, bye-bye. It doesn't go back into the account. That's called simple interest. So your investment stays the same, R. But the interest over the years is just accruing, right? We'll call that accruing, okay? And the speed at which this goes is, of course, the interest rate, okay? So the interest rate is an angular velocity, okay? All right? So any kind of thing where the resource itself stays constant, is can be modeled in this way, this submanifold. Now, again, this looks trivial, right? But it really isn't, because of the way we choose the coordinates as a return. So this is an angle. All right? Now this insight lets us generalize to those other shapes. And in fact, this insight lets us generalize to crazy stuff, like SO3, huh? So, all right. So that foundations I want to lay, and then we'll do the rest tomorrow. All right? Tomorrow or next week. So let's go on. So I did this. So what you can see is if you start here, you have no production, you'll go over there. If you had a bigger piece of land, you would go over here. So if you connect these together, you will see that what you're really doing when you're producing is you're shearing. It's like a group of transformations where you take the whole plane and you shear it like this, right? So you could imagine going out there and shearing further. You'll have some other asset here, a -1. What is a negative? What would that be?
It's borrowing.
Yeah, so this is an asset side. This will be your liability. And while you're receiving interest here, you're paying interest there, right? And look at the balance, your assets and your liabilities balance, right? Your interest receipts and the others, they also balance, in this case, because they're the same. All right? Actually, you got your first rigid body because you got this thing moving there, you got this thing moving there, and all right? Okay. Now, an accountant would put the assets on the left and liabilities on the right, but you'll be able to flip that around. That's a question of definition, right? Okay. So better would be to call this the debit side, and this the credit side or something. Or the asset side and the liability side, and then you can decide which one you want to call plus and which you want to call minus. All right? So it's a shear. And what shearing does here, and so the shear, that's the transformation you're doing. So we're getting close to transformations, you see? What it does, it shows you how you produce stuff, how you grow crops or produce things or produce interest. That's what the bank does for you. All right? And in order to take that thing, you calculate this thing, which I call arc length, which is just the amount of interest, and you divide it by your capital, right? Okay. All right. Let's see if we can. So this is the easy one, right? But this is a non-trivial problem in economics, okay? So it's a non-trivial thing to say that land, look at the theory for land and stuff. It's quite complex. I don't know. Do we have an economics student here? Did you have to study your econometrics? And I don't really worry about that. Yeah. So it's a very pretty thing. And also that the asset and liability sides come out. So you can already see this working, okay? This is going to work, all right? I'm going to give you another example. That's what I call amortization, right? So how should I do this? Oh, yeah. I can stay with land. You can stay with land and go through the cycle. I won't do that. Let me go and look at chickens and eggs. So I'll call these eggs and I'll call these chickens. Okay? So you're a chicken farmer, all right? And you got this pile of chickens. And these chickens, they lay eggs and they die, all right? And then okay, and this is some average amount that you have, right? So I don't know, 0 chickens is somewhere out there. It doesn't really matter. You can call that 0 too. Then you'll have negative chickens or something. But we're not going to try to do that. And you start off with this, you're full up with chickens, and there's no eggs. So these chickens start producing eggs, but at the same time they're dying, right? So you can imagine you're going to end up here, right? Okay? And then if you think a little bit, we won't do this now, you can keep going on and you can see this as the credit cycle and the debit and blah, 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 the crop cycle and this, all right? What I want you to see is that this is what they call amortizing. This word more, that means death, huh? In Romanian, huh? I'm sure, huh? Right? Huh? You guys have a Latin language, right? Huh? So this means you're just killing it, right? Huh? And, they die. Huh? That's basically what's happening, right? Huh? So it's called an amortizing. I call it amortization. All right. So things are producing it, but it's dying off. All right. Huh? Okay. If you have an annuity, you know what an annuity is? That's what you get when you buy a house. Right? So they give you this annuity, and what you need to do is you have a period of, say, 10 years or 30 years, I don't know what you do, to pay this off, this annuity. So when you start out, you have, this is the amount you borrowed. You know, that's the amount on your mortgage, right? Huh? Then you have to pay some interest to the bank, all right? But not only that, you also have to repay part of that loan, right? Okay? So first you go up, that's the interest, and then you repay part of the loan, right? So you end up at this point. Right? Then you have a little lower loan, so you pay a little bit less interest, and you can pay off a little bit more of the loan, right? Huh? And this process continues until you're here, and you don't have to pay any interest, and the last payment is all amortization, right? Huh? And you've paid off your loan. That's called an annuity. So what is the thing that's now keeping you on the submanifold? That's your contract, okay? So if you don't pay off or you don't pay your interest, you're in court, okay? And they grab your home and the whole game is up. So you're not allowed to go here, you're not allowed to go there, right? You're on this thing. Here it was nature telling you, you just don't have any more land, bud, right? Huh? Here it is, the law telling you, huh? You're going to go to jail and you're out of the game. Huh? Okay? You go to debtor's prison. All right? Huh? So it puts you on the submanifold. And now you see that an annuity or these chickens or regular farming actually also works like that because you have seasons. Huh? So this is your harvest, and then you got to plant, and then you got to plow, and then you got to plant. So you go negative on your seeds, and you go run. So this is like the I don't know, the fall. This is like you don't know. You can have your 4 seasons. You know, that's the origin of the circle, I'd say. You know, actually, it's the sun turning around, creating these seasons, and us creating farming. You know, so this is not going like this. This is more going like that, and then going up. Huh? All right, oh, complicated. Huh? All right, huh? Okay. All right, so this is a rotation, right? So paying off your loan, your annuity, you're just rotating. And rotation is our geometric description of amortizing. Huh? Right. So rotation is an amortization, right? And you do that for an annuity. And what you do is 2 types of payments. You have these interest payments, so, where you get these eggs, eggs plus negative chickens, right? The repayments, with eggs. So this will be eggs and deaths or something, retirements. I don't know. If you want to avoid that word, then you're on YouTube. Okay. Now, what is the return here, right? That's kind of funky because you would think it's only the eggs that matter, but it really isn't because the return to the bank also includes the repayments, right? So the total return to the bank is not only the yield, but the total yield is what they got here plus the repayments. If you didn't do your repayments, they still wouldn't be happy, all right? So you've got to add these things up, you know? So if you figure that out, you'll see that what the total return is exactly this arc length here, right? A little bit up, a little bit like that, huh? All right, huh? Okay, that's the arc length. So your total return is this arc length, which is now this thing, divided by that same R, your resources. All right? Okay? And that gives you the angle, which is now your return. Well, it's more complex, but it works. Huh? We also have defined what we mean in this situation by capital and resources and why that's fixed. You know? So apparently there's this one number that remains fixed in this motion, and that's this number R, right? Because, and the way we set it up, it's a perfect circle, so you're squaring this and squaring this. But maybe we have to, this is all money and this is money, and you know, it will work out, okay? But you got to get the units right, and if you don't, you're going to have some factors and it will look like an ellipse, but that's not going to change the story.
Does there has to be R has to be fixed, or because if you have like the fields where you grow every year?
No, it doesn't. I'm just saying in this situation. Huh? If you grow, we'll come to it later, then this point starts moving, or you know, all kinds of things can happen. Well, let's start small, right? Huh? No, you're right. Huh? It doesn't have to be. I'm just looking at situations where it is fixed. Land is fixed. In this annuity, it's also fixed. They have things they call prepayments. They allow that you pay a little bit more, but I'm ignoring all that, right? Huh? You see? First, I want to get lucky, and then I'll make it more complicated, and then see if I can get lucky again, and then that's the game. But first, let's look at simple things. Yeah, but thanks. Huh? You see? The message you got to have is that the rate of return is an angle, okay? It is. In the most general of cases, it will be, all right? The notion of angle, though, is way more general and structured than the idea of a return, all right? And we'll see we can get returns in very complicated situations, okay? So hold on. Huh? I have a little bit more time, so I wanted to finish off with looking at growth, okay? So growth is a thing all economists always do, right? So what they do is they look at, say, population growth or something, and they assume it is exponential. Now, how do you get that out of there? So you'll start off with your population, that's R, right? Huh? And then a bunch of kids are born, right? Huh? And these grow up, so that's the first step. Second step is they grow up and they join the population, right? Huh? I'm now assuming everybody lives forever, right? I can deal with that later. Huh? Now you have a bigger population, they get more kids, and those also join, right? So first step this, second step that, third, okay? Whoop, 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 whoop. If you sort that out, you'll see you'll go on a hyperbola, all right? And your initial capital, what you would say, your initial starting point, the population, is precisely this difference now between these two rather than the sum. And sort it out. You'll see it works, okay? So those are the three like basic shapes that you can make. And again, what is now the arc length? The return is this whole arc length. So that's our coordinate will be this arc length divided by this r, right? The new, this original population, right? So that's the current population corrected for the birth in this funky way. Arc length will be not only the interest you receive, but the interest you receive upon interest, right? That's what you add up. So you have interest plus interest on interest, and if you do that, you plug that in there, then you get what's called a hyperbolic angle, okay? This is called a twist or shearing angle for production. This is called a regular elliptical angle because it can be ellipse. And this is called a hyperbolic angle. You have a hyperbolic sector. You can all look it up in Wikipedia, all right? But it's just this arc length here divided by r. So this is a total stuff you get physically, and you divide it by that to get the percentage, okay? Again, I will see that this is exponential growth. This is also an exponential growth, believe it or not. Huh? And this is also, of course, an exponential growth. And you'll already see that one coming because you know the complex exponential does the right job, right? Huh? You already see that if I have this angle, the e to the I theta tells me exactly where I am, right? Here you'll see a similar formula, and here you'll see a similar formula emerging. You say, how can this be exponential? But it is, but it is, but it is. Everything is exponential in this setup. All right? Let's call the exponential map. So just in concluding, I just made this little slide for the tangent space. And this is when I had to rush here in order to go and give this lecture, but I think it speaks for itself. You see, but although these manifolds are complicated, the tangent spaces are simple, right? They're all aligned, okay? At every point, you'll have this line, all right? Here, here, same one with this one, same one with that one. And this coordinate is what is the angular velocity, so you plot it on here. So here's the Q, here's Q dot. Well, let's put Q dot here. Here's Q. And this is then in percentages, or radians if you want. And this is in then percentage per. If it's a circle, radians makes sense. So I guess radians will make sense everywhere, right? That's a radian is exactly how many times you can fit the radius. So that's precisely the moment, what they call capitalization point or the break-even point, right? When you've earned back your capital, when the combination of interest and amortization has earned you your capital, that's 1 radian. I forget how they call that in capital theory. Is that the capitalization rate? Oh, something like that, right?
Recapitalization.
What?
Recapitalization.
So what do you say when you the time it takes to earn back your initial investment? You know, so the repayments plus interest. There is a name for that.
Break even, maybe?
Break even, something like that. So the radians, if you measure this in radians, it's the break even, right? Because this is what you had. And what is a radian? You just try to fit the radius on the arc length, right? That's why you get 3.1 times, because of 3.14, you know. So that's your break-even points are the radians. So if you measure your return in radians, you measure return in break-even points, right? That's interesting, huh? You just got to see how these things are. You know, that you can think of rates of return as angles, and then of course the return as angles and the rates of return, they live in the tangent space and they become the angular velocities, okay? And the rate of return can be an enormous number. It doesn't matter, it's not constrained by anything, right? The angle here, yeah, you exactly have 2 pi break-even points on this one, right? Okay. So it's limited. This one, I guess you can make any, but yeah, make anything too. All right. All right. So this is, so we came a long way. And we're going to go way further. So I'll work this further out, and then I'll do the exponential map for this simple case, okay? And show you that they all can be written as an exponential. The exponential map does the following. It says, okay, I know where I'm here. Now, where will I be so many times later if I only knew this, okay? So if I only knew at what rate I'm buying, and I'm going to continue doing that, right? So that is a unit velocity. Where am I going to end out, right? So that's partially answering this question that was posed in the beginning. How don't you know what the forces are? Well, I first have to determine what is a unit velocity, meaning a free motion. So the thing that determines free motion is the exponential map. Right? So free motion can be exponential growth, free motion can be linear growth, and free motion can be this kind of amortizing rates, okay? And it's all determined by the exponential map, okay? Right? So with that, I'll terminate this lecture and hope I got you excited enough to attend next week.